In this video, we're taking a look at Boolean algebra, that is the algebra of zeros and ones. We will look at single variable properties, 2 and 3 variable properties, and then apply those properties to the simplification of logic expressions. And we will finish up with a graphical method, which is called the Karnaugh map. Here is the statement of the axioms of Boolean algebra. The first statement is that 0 and with 0 is equal to 0, and 1 or with 1 is equal to 1. Note that those two expressions here are combined together as axiom number 1, and they are duals of each other. And what we mean by duality is that the zeros get replaced by ones, and the and gets replaced by or. And then the same statement is true first with the 0 and 0 equals 0, and then the dual of it, which is 1, and then the and replaced by or. And so 1 or 1 is equal to 1. Second axiom states that 1 and 1 is equal to 1, and then the dual of it, 0 or 0, is equal to 0. The third one, 0 and 1 is equal to 1 and 0, and that is equal to 0. And then 1 or 0 is equal to 0 or 1, and that's equal to 1. And finally, looking at the complement or inversion of the variable, x is equal to 0, and so therefore x naught is equal to 1. And if x is equal to 1, then x naught must be equal to 0. So this is the algebra of variables that just take on two values, 0 and 1. So here is the statement of duality shown again. Given that logic expression, its dual is obtained by exchanging the plus, and which is the or, and the and operators, and by exchanging zeros and ones. And here is a little example, as we have just looked at before. 0 and 0 is equal to 0, and the dual of it is 1, or 1 is equal to 1. From the axioms, we can derive the single variable theorems, which are x and 0 is equal to 0, x or 1 is equal to 1, where x can be either 0 or 1. Then number 6 here, x and 1 is equal to x, x or 0 is equal to x. So in both cases here, we get the variable x back. Number 7, x and x is equal to x, x or x is equal to x. Again, x is a variable which can take on values 0 or 1. Then x and x naught is equal to 0, x or x naught is equal to 1. And finally, x complement and then once more complemented is back to x again. So x naught and then the naught of x naught is giving us back the original variable. Things get interesting when we start combining 2 or 3 variables and look at the properties based on the axioms of the Boolean algebra. So x and y or z, where y or z is in parentheses, is equal to x or y, x and y, or x and z, the distributivity property, that is. And we have the dual of that, where we replace again the and by the or, and the or by the and. Since x, y, and z are just general variables, we are not changing anything here. So the x or y and z is equal to x or y and x or z. Then the combining property, x and y or x and y naught is equal to x, and x or y and x or y naught is also equal to x. This property of combining is going to be important for minimizing the cost of logic functions or logic expressions. Okay, you can see that on the left we have two minterms, x and y, or x and y not. On the right, we just have a single term. And of course, going back to the properties of Boolean algebra, where this came from is that x and y, or x and y not, can be written using the distributivity property x and y or y not, like this, and then y or y not that is equal to 1. Okay, so that was a single variable property. And then x and 1 is another single variable property that just gives us back x. Okay, so that would be a way how you can prove this combining property here. And then De Morgan's laws, which we have been looking at before, x and y inverted is equal to x inverted or y inverted, and then x or y inverted is equal to x inverted and y inverted. Another way to prove properties of Boolean algebra based on the axioms is known as perfect induction. Okay, and that just simply means that we try all possible combinations of zeros and ones and show that the left side of a statement and the right side of a statement are equal. Okay, this is a nice property of working with just binary variables. We can, in principle, always write out the different expressions and make proofs in this way. So in this case, we write down all the three variable properties, or all the three variable combinations, and we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, etc. up to 1, 1, 1. And then we check what y or z is. So y and z are over here. So when both are 0, we get the 0 here. When one of them is 1, or both of them are 1, we get 1s. Again, when both are 0, we get the 0, and down here we get 1s again. So we have this combination for the y or z. And then we AND that with x. So when x is 0, we're certainly going to get 0 when we are ANDing. So we have 4 zeros here. Then we have a 0 here from the y or z. So that transfers over here. And then finally, the last three of those, we have x equal to 1 and y or z equal to 1. And the end of that is going to be 1 again. And then we show the right-hand side of the distributive property. And that looks at x and y. So we go back over here to our enumeration of the input bits. So x and y can only be 1 if both inputs are 1. So we are down here, 2 1s here and 2 1s here. So that gives us those 2 1s at the bottom here. Then we look at x and c. And the same thing is going to happen here. Only when x and c are both 1, we're going to get the 1 as a result. So x is 1 here, c is 1 here, and x and c are 1 here. So we get this one and this one. And then we OR the two together. So we get a 1 back here whenever at least one of the two columns here has a 1 in it. And that gives us the 3 bottom ones. And so what we find is that we have 3 1s here from the left-hand side of the expression, 3 1s here from the right-hand side, and the rest of it 0. And so that proves that this expression here is true, which is the distributivity expression. So now we can take a look at the cost of a logic expression. The goal is to eventually find the lowest cost for a particular given logic expression. And the way we define the cost is the total number of gates plus the total number of inputs to all gates. And if we make a little example down here, f equal to little m0 plus little m2 plus little m3 plus little m5. So those are the min-terms, m0, m2, m3, m5. We assume that we are using 3 variables, x2, x1, and x0. So m0 is x0, x2 inverted, x1 inverted, x0 inverted, and then AND it together, or with x2 not, x1, x0 not for the m2 term, and so forth. So we get those 4 terms. And for the counting now of the cost, we have an AND gate here with 3 inputs. We have another AND gate here with 3 inputs, another AND gate with 3, and another AND gate with 3 inputs. So altogether we have 4 AND gates in here with 3 inputs. And then we also have an OR gate that connects the outputs of those AND gates together. So we have an OR gate that goes all across here. So that makes 1, 2, 3, 4, and then a 5th gate for the OR gate. And then we also have the inversions here. Each of the variables needs to be inverted. So we get 3 more gates. So altogether we get 8 gates for this expression. And then we have to count the inputs. So we have from the 4 AND gates with 3 inputs, that gives us 12 right there. And then we have 13, 14, 15, 16 for the inputs of the OR gate, the 4-input OR gate. And then we still have x0, x1, x2, the inverters there. That gives us another 3, so that gives us 19 inputs here. And then we add 2 together, so we get the total cost of 27 for the implementation of this function here without trying to do any kind of minimization. So here's a quick picture of what that logic function would look like. We have the 3 inverters for x2, x1, x0, so the outputs are going to be x2 naught, x1 naught, and x0 naught. Then we have the 4 3-input AND gates, and I did not label here the inputs, but for the first one it would be x2 naught, x1 naught, x0 naught, so we would take the outputs here from the 3 inverters. For the next one it would be x2 naught, x1, x0 naught, so x2 naught would come from here. x1 would come directly from the input before the inverter, and x0 naught would come from the output of this inverter here. So we can count again how many gates. We have 1, 2, 3, 4, 5, 6, 7, 8 gates. And then we can count the inputs 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So that is an easy way to find out what the cost is by just sketching the logic circuit that implements the function. So now to find a low-cost implementation of this particular function here, we are taking a look at the different terms and we check whether we can combine some of those things using the 2 or 3 variable properties that we have looked at before. In particular, the combining property, which was stated as x times y plus x times y naught is equal to x, is a property that we want to make use of. So here we have 3 variables, so what I'm calling x in the general property here might consist of several variables. In this particular case, we can see that we can combine this term here and this term here into something simpler. So both of them have x2 naught and x0 naught in them. So we pull that out using this distributivity property that's shown here. And then we multiply this or AND this with x1 naught plus x1. So the x1 naught from here, x1 from here. And of course, that's going to be equal to 1 using one of the single variable properties. And another single variable property is that x2 naught, x0 naught, and 1 just gives us x2 naught and x0 naught. And then similarly over here, we find that we can combine between those two terms. We can combine the x2 naught x1, which comes from which is present in both of them, and then using distributivity property again, and it with x0 naught or x0, which is equal to 1. So we end up with this simpler term here rather than those two terms. Now, one of the things that's interesting with Boolean algebra is that you can actually take one of the terms, like the one here, you can take that and incorporate that more than once in some of the combinations that you use here. So that would be different if you were to do regular arithmetic over decimal numbers and the regular sum. Because x or x is still x, it actually doesn't matter that we have been using this term here twice. And then the last term, if you look at this one here, you find that it does not combine with any of the others in the same way like those two did. Each of those other terms has at least two things different between here and here. The first one, for example, has x2 and x0 different. The second one has x2, x1, and x0 different, so all three terms are different. And then with the last one here, x2 naught and x2, that's different. x1 and x1 naught is different. x0 would be the same. So two things are different here, so we cannot combine those with the combining property. So combining what we have been doing here, we now find that the function, the same function, can be expressed in a simpler manner as x2 naught and x1 naught, or x2 naught and x1, or x2 and x1 naught and x0. The simplification has brought the cost down because now we have 1, 2, 3 AND gates, two of which have 2 inputs, one has 3 inputs, and then we have an OR gate with 1, 2, 3 inputs. We still need the 3 inverters for x0, x1, and x2. And so we find now that we have altogether 7 gates, the 3 AND gates, the OR gate, that makes 4, plus the 3 inverters, that makes 7, 13 inputs, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for the OR gate, plus 3 for the NOT gates, so that makes 13 altogether. So the cost has come down now to 20 from our original value, which was 27. So now we have to take a look at this a little more systematically and try to find out what was the key to reducing the cost. And we can see that the key thing was that we had, in the case of 3 variables, we had some xi, xj, which were the same, and then somewhere some third variable, xk and xk naught, so one of those is the complement of the other. And then we use the distributivity property to write this expression over here as xi and xj, and then AND it with the combination or combination of xk or xk naught. Okay, and then we use the single variable property where x plus x naught is equal to 1, and then the property where x times 1 or x and 1 is equal to just x. So we get the xi, xj. So the key thing is that xi and xj and xk and the other expression xi and xj and xk naught were differing in only one position. If you do this numerically, for example, 0, 1, 0 and 0, 1, 1 would be a case where we just differ in the third position, or 1, 1, 1 and 1, 0, 1, we only differ in the middle position. So here is an example. We use again 3-bit terms, and we show for this x2 naught, x1, x0 naught term, we show all the possible ways how we could reduce that into an expression of just two things if there is another min term ORed together with them. Okay, so on the left here we have x2 naught, x1, x0 naught for all three expressions. And then on the right, we take those expressions that differ in just one position from what we have here on the left. So I started out here with the middle position, x1 here, x1 naught here. And so we end up getting x2 naught and x0 naught as the expression for the sum of, or the OR of those two min terms. Since there are three positions, we can look at the difference in each of those three positions. So the last position here, x0 naught, x0, if we combine those two min terms, then we get x2 naught, x1. And on the last one here, the first bit is differing between the two min terms. And so we can combine those into x1 and x0 naught. Okay, another way to look at this is to put this into a neighborhood arrangement where we try to show this original term, that was the term here on the left-hand side. We show this term, and then we just show to the left the one where the middle term is different, to the right the one where the first term is different, and at the bottom here the one where the last term was different. Again, because we have just three variables here, there are three neighbors that are just distance 1 away from the original expression. If we express it directly in terms of min terms, then it would be that min term 2 has a neighbor which is a min term 0, another neighbor which is min term 6, and a third neighbor which is min term 3. Now min terms and max terms are related to each other through inversion and De Morgan's law. And so we can actually do something similar with the max terms as we just did with the min terms. So this is the same bit combination that we're looking at, but now we're looking at the max term. So we have x2 or x1 naught or x0, whereas before we had x2 naught and x1 and x0 naught. So this is the common term that we're looking at, and then to the right we're looking at terms that are distance 1 away from that. Okay, this is the combining property, the dual of the one that we looked at in the previous slide. So here we have x2, x0, x2, x0 common in both of those expressions, and only x1 naught and x1 are different. So the result is x2 or x0. It's basically coming from those terms here, which were the same in both of them. And then again, because we have three terms, we just have three possibilities of having one of the terms different between the two expressions. So here it is the last term that we assume is different, and then the x2 plus x1 naught, those which are the same, is what we get here as the result after combining. And the third one is just simply the first term, which is different, and the last two, which are the same. And we see here the last two coming out through the combining property. We can again show a neighborhood arrangement. So we have here the original term, which was the one here on the left, and then we have the term to the left here, which differs in one position, the middle position, the term to the right, which differs in the first position, and the term here below, which differs in the last position. And we can write that in terms of the max term expressions, capital M0, capital M2, capital M6, etc. So the neighbors of capital M2 are capital M0, capital M6, and capital M3. And we could do this for any other term. We could take the term M1, for example, and look at the neighbors of it. We could take the term M4 and look at the neighbors of it, and so forth. So now writing out the variables every time and checking which positions are different and so forth gets a little cumbersome. And there is a nice graphical method which is called the Karnaugh map that actually captures those neighborhood relations in graphical form, in the form of those little tables that we have down here. This is the one for the min terms, and over here is the one for the max terms. So the Karnaugh map in general is an alternative to the specification of a logic function by a truth table. And the key thing is that it preserves the neighborhood relationships between the bit pattern. And by neighborhood relationships, we again mean that those terms which only differ in one position are neighbors of each other, and that this neighborhood is preserved in the graphical layout of the Karnaugh map. So we start out here at the top row with writing down the 2-bit combinations 0, 0, 0, 1, and then notice that we go now to 1, 1, not to 1, 0, and then after that to 1, 0. So this arrangement of the bits here in the row above the table is such that as we move from one combination to the next, there is always a change in only one bit. So from here to here, there is the second bit which changes. Then if we go from here to here, it is the first bit that changes. And as we go from this 1, 1 to the 1, 0, it is the second bit that changes again. And actually, it wraps around at the end from the 1, 0 back to the 0, 0 again. And here we have a change of this first bit with respect to the first bit here. So you can think of this as wrapping around and writing down the bit combinations in such a way that there is always a change of only one bit as we move from one position to the next. On the left-hand side, where we only have one bit, trivially, we just go from 0 to 1 and then back to 0 again, so there's only one bit changing. And then we can fill in this table, in the different slots, we can fill in the names of the min terms. So here we have 0, 0, 0, so that corresponds to min term M0. Here we have 0, 1, 0, so that corresponds to min term M2. Here, for example, we have 1, 1. If we go to the bottom here, we have a 1 here, so this corresponds to triple 1 here, and that is min term M7. If we look at the last column here, so 1, 0, 0, so this is the slot for 1, 0, 0, that corresponds to min term M4. And then at the bottom here we have 1, 0, 1 because of the 1 over here, and that corresponds to min term M5. And fairly simply, the max terms are labeled with the same indexes as the min terms are. So we have here max term M0, M2, M6, M4, and so forth. And you can also see in here that we have actually those patterns that we had looked at, those neighborhood patterns that we had looked at before. They appear in this table here for the max terms, and they appear in the table here for the min terms. Okay, that's actually how I chose to arrange those on the previous slides to show the neighborhoods between those bit patterns. So now finally, let's look at this example again. We had this f equal to x2 not, x1 not, x0 not, so that was min term 0. Then here we have min term 2. This is min term 0, 1, 1, so that's 3. And here is min term 1, 0, 1, so that's M5. Okay, so we fill those three bit combinations in. So the M0 is here. Okay, then the M2, that's 0, 1, 0, so that goes into this part of the table. M3, that's 0, 1, 1, so that goes down here. And the M5, 1, 0, 1, so that goes back here. Okay, so I put the 1 in each of those positions in the Karnaugh map, and implicitly in all other places we are having a 0. Let's fill those in. Okay, again, if we work with Boolean algebra, we only have zeros and ones, and whatever is not the 1 is going to be a 0, or vice versa. So now using the Karnaugh map, we can see that those two 1s are neighbors of each other, and looking at the reading off the bit pattern from the Karnaugh map, we can see that x1 could be the 0 or 1, so we don't care about that, but x2 has to be 0, so we have an x2 not, and x0 has to be 0, so we have an x0 not, so that's this term here. And then we look at the neighboring bit patterns here. So this happens when x2 is 0 and x1 is 1, so that's x2 not and x1, that's this term here. And it doesn't matter what x0 is for those two patterns. And then finally, the last one back here, that sits all by its own. It doesn't have a neighbor which is 1 either above or to the left or to the right with wrapping around. And so we have to take this one as it is. So we take it from up here directly down here, because we cannot combine that with anything else to make a simpler expression. And what we see here is, of course, that we get the same expression back that we had seen earlier when we just directly applied the Boolean algebra properties.